come in late, well, the good thing is that I guess they have the recording available so they can catch back up on the beginning. Okay, so today, this afternoon, we're going to continue our discussion on active filters, which is the second to last major topic that we have, and the last topic that we will do in the course will be the feedback amplifier section. All right, so we're getting here. We're in week 9 and we're making progress. So let's talk a little bit about the active filters. Last week when we started, we did the first order filters, which was an op-amp and a simple RC network in front of the op-amp. That is, and the op-amp part is what made it active. And we saw that the reason for the active filter part was that the active filter allowed us to have some gain on the device because the RC network would attenuate the signal, so to get it back up to some sort of level, or maybe even to boost it to another level that you may want to use, you would use the op-amp part, hence the term active. And usually the active filters are only resistors and capacitors that we'll be considering. So continuing along that vein, in many applications, and probably in most applications, the first order filter changes too slowly from the pass band to the stop band. Remember that terminology. The pass band is the sort of set of frequencies below the cutoff that the low pass filter, well, I'm talking about a low pass filter in this case, that it allows to get through. And then the stop band is where it stops everything. The high pass filter, of course, is the flip around. So what happens is that in many cases, and maybe in the majority of cases, what you need is a response looking more like the red line, which is a sharper, it goes up to the cutoff frequency, which is in this case is 100 radians per second, and then changes fairly quickly. The one in the blue line, which is a typical first order response, you know, there's a long transition from stop band, from pass band to stop band, which means too that some of the things that you don't want, which is what a filter is supposed to do, get rid of the things that you don't want, still a significant portion of that is going to be allowed through. So what we need to do is to change that transition rate and crank it up. And we do that by adding more resistors and capacitors to the network. So if we add two more passive components, one resistor and one capacitor, then we create the filter that we have below. Notice how it's added. The amp is kind of flipped around a little bit, but the same original RC network that we had above, right, which is now designated here as R2 and C2. Those were the original jobs. What we've added are two extra components here. A capacitor, that feedback capacitor now that is going from the output back to the beginning of R2, and then a new input resistor, R1. Because we have two capacitors in the circuit, of course, now we're going to have two poles. The capacitors have that 1 over SC behavior. So it keeps adding, oh, that's bad, 1 over SC, right, behavior as the impedance. So that keeps adding poles. Every time you add capacitors in a filter of this design, you keep adding poles to it as well. Okay, so let's proceed and analyze. Now, there are all sorts of there are many amplifiers and many designs and many approaches to this. So we're taking a sort of middle of the road approach, giving you some things that at least for our level, one, they could be fairly easily implemented and understood, and then two, you're able to one, analyze it, of course, and then two, later on design it and use it practically. These versions of the active filters use one op-amp and the components alongside. Later on, tomorrow, please God, when we meet, we will see how to cascade, which is a question somebody asked since last week, if we can make higher order filters by cascading, and the answer is yes. So we're going to use those in tomorrow's class. All right, so here it is, and you asked to drag back something that you all probably dislike a lot, which is Kirchhoff's laws. including, well, and the particular one that we're going to use is the current law. So you look at nodes A and B, and you sum the current going in and out of each node, right? So for node A, you have the equation here, and you can always double check that when you're checking over the slides and the recording. So the current then equal to the sum of the currents out, or the current into the node is equal to the current going out, and then node B here. And then first off, to do my simplification, at this point in time, instead of using like 1 over SC1, I'm using Z1 and Z2 in the manipulation, and then you will substitute down to the n. Right, so instead of having these 1 over this, 1 over that kind of thing, it makes it a little bit easier. And then, of course, to analyze this, make use of the fact that the voltage at node B is in fact the same as the output voltage. The op-amp is acting as a unity gain buffer, so that the output voltage appears at the non-inverting, sorry, at the inverting input. And of course, we know because of the behavior of the op-amp, that will be the voltage appearing at node B. So if you know that, right, then the thing is that you have to eliminate VA and VB from the solution, then substitute for Z1 and Z2, and then carefully simplify. Now, I'm giving you this. This is going to crop up in a little problem set coming up shortly, to prove that when you do all of that, you're going to get the answer down here, right? And now I'm saying carefully because it takes, there's a lot of algebra to do, to write it over, to simplify it, to substitute, and to make sure you don't make any errors. Okay, so when you get to that point, of course, once this is in the Laplace domain, and we know to get the frequency response now, the frequency transfer function, or the Fourier transfer function, we make the substitution S equal to j omega, and we get A of j omega is here. And the point I was making for those of you who were in the signals class this morning, keep the j omega in brackets, right? So when you square it and cube it and so on, sometimes the j will disappear as a minus, because if it's squared as it will appear as a -1. Other times it will be there as j or minus j, depending on the power, right? So keep that in a bracket. And the other thing to help with this simplification for this approach, as I said, there are a number of other approaches to take, and we will see another approach tomorrow that is easier but has its own drawbacks. You're going to let the two resistors 1 and 2 be equal to some common value R. You're going to let C2 equal to some value C, and C1 is twice that value, okay? So C1 is twice C2, and R1 is equal to R2. Okay, when you do that, you create a particular version of the filter, and we had the name last time. We create a particular version of the filter called a Butterworth. Right, and I'll talk that will come up shortly. So you do that. Of course, if you have any questions at this point in time, or at any point in time, just let me know. Yeah. So when you do that, you and make the substitution, you're going to get a transfer function, a Fourier transfer function, looking like the one in that sort of brown or orange, depending on what sort of color your screen is, box. Now remember the passband. When we define the cutoff frequency, it is the point at which the magnitude of the response drops to 0.707 times the value of the passband, or 1 over √2. So we need to find out what is magnitude A j omega, set that equal to √2, so that we can solve for the thing that we're trying to solve for is this. We want to find out what is the cutoff frequency. In other words, what is omega C? So again, if you juggle around, if you substitute and you solve, right, the magnitude of A j omega, and probably I should have put that in some magnitude brackets there, is that is a complex number. So of course it's the square root of the real and the imaginary parts all squared, which was why you had to keep that j omega all squared in brackets separate from the rest, because part will come real and part will remain imaginary. So now when you do that, you're trying to solve for omega at this point in time. When you do this and square it up, you're going to get omega to the fourth. Okay, so when you get omega to the fourth equal to some big funny expression here, when you solve that using the normal quadratic formula, you're going to get an expression for omega squared that is plus or minus some values. All right, we will deal with the real value. So when you get omega squared equal plus or minus some value, you're going to ignore the negative one and go to the positive one, and then take the square root of that to get omega. Yeah? Everybody following that? Omega fourth is going to give you two sets of answers. Two sets for omega squared, and out of that, you're going to take the positive values and then take two, and then from that, you're going to get a plus or minus omega, and of course, is a positive one that we need. Make sense? Yeah? And then the next design, the next bit of analysis a little bit later on in the class that I show you is going to show you a different approach for doing it. But it's always good to have more than one approach to compare. If you do all of that and you don't make any mistakes, you're going to get that omega c is, well, if you do it that way, you'll get it as 1 over root 2 RC, right? Which I'll rationalize in this form. Why? Because sometimes when you're writing, you may inadvertently do this. Okay, or you might forget with your own handwriting and so on. So I prefer to keep it this way. Yeah, the square root is kind of separate from everything, so it's root 2 over 2 RC. It's a little bit clearer, or you could put RC root 2, which is another way. But just whatever you do, try to avoid this. Okay. So the cutoff frequency is root 2 over 2 RC. And this particular design, it is a very standard, well-known design named after the people who came up with it hundreds of thousands of years ago. It's called the Salin key version, or because of the way the op-amp is used, it's called a voltage-controlled voltage source, right? Voltage-controlled voltage source is kind of like a fancy way of saying an amplifier, right? A voltage in, voltage out in here, which is what we're using. But in later courses, if you do, for instance, a network synthesis course, any of you all, you'll delve into this VCVS and see exactly why it is called that. Okay, but for want of a better word, it's just a fancy term for an amplifier. Voltage in, voltage out, a voltage-controlled voltage source. The transfer function, as I mentioned, by making that substitution, a MOSFET can be, the voltage-controlled voltage source, yes, can be created using a MOSFET and some associated components. All right, not a bad observation. Yes, it can. Right, so by making that particular, what do you call it, the substitution that we made, where we made the 2 R's equal and we made C1 equal to C2, we created a particular type of transfer function, this one, right, that is called a Butterworth transfer function. It has to do with the coefficients and so on. The thing about the Butterworth response is that it produces something called a maximally flat response. And if you remember last time when we were talking, we said that they just draw over this here a little bit, that filters can go from the pass band to the stop band in all sorts of ways. They can do it like this. They can be very flat here and then suddenly change, right? But you always have to adjust one. You have to trade off basically this transition against how it performs in the passband. The Butterworth and the maximally flat give you a behavior that in the passband itself, all right, so if you look at the passband is as flat as you can get for a response. And then it changes from the transition frequency, at the cutoff frequency, it changes from pass to stop band. But of all the filter designs, of all of the possible arrangements for this, and there are many, and we'll come up with another one tomorrow just to show you, that the Butterworth gives you the flattest response. But the trade-off for that is that this transition here is relatively shallow. There are other filters that give responses that look like this. There's a little ripple here, and then it sharply changes. So these now give you a ripple in the passband, and it suddenly changes from passband to stop band, but then you get the ripple. Right? And you remember I was talking a little bit about that when we spoke about second order responses, which is going to come up shortly again. So you have to pick your battle as an engineer. Do I want a flat response in the passband? But the thing is that when it's going from passing the frequencies to stopping the others, it is going to change fairly gradually. Or is my application such that I really need it to change sharply from passing to stopping? And I'm going to take the trade-off with the fact that I'm going to have some little amplitude variations in the passband. Right? Those are the kind of things a designer has to cater for. So for instance, maybe in a hearing aid, right, where you're stopping certain frequencies outside of the audible range and so on, but you want them to, whoever is the user of the hearing aid, to hear all the passband frequencies relatively constant. You may use the Butterworth type of design. But if you're dealing with a situation where you have the signals that you want are very close to the ones that you don't want, then you're going to sacrifice a little bit of ripple by making the transition from passing to stopping very quick. All right? Those are, like I said, those are design considerations, and they are probably about as many fingers and toes as most of us have in terms of the types of transfer functions that create the filter responses. Okay, and there are all sorts of things, and I'll talk briefly at the end of it all about some of the things that you tend to look for. All right. So maximally flat, and if you look at the expected response, therefore, the response is a flat response until it reaches omega c. Right, omega c, of course, the response drops by 1/√2, which is 0.707, and then it decays at 40 dB per decade. Remember, the first order filter decayed at, and we covered it again this morning, minus 20 dB per decade. Right? Right, the first orders decay at minus 20. So a second order, and we'll prove it in the signals class tomorrow if those of you doing it, that the second order will decay at minus 40. And of course, a third order filter, which would have had something like an S cubed in the denominator, would decay at minus 60 dB per decade. And so you keep going on. All right. It's not too unusual to have in the analog domain, right, maybe 5 and 6 order filters coming up. They start to get some strange behaviors after that. In the discrete time domain, the signal processing domain, it is not unusual to have orders of filters as high as 50. All right, and if you do discrete signal processing with me, in year 3, any of you all, we will spend some time talking about discrete filters and that kind of thing. And I will, well, of course, recall this having done it with you. Yeah. So if you were to actually generate one, here's one that is called a normalized second order low pass filter. Normalized means that everything is set, the cutoff frequency is set to 1 radian per second, right? As we said, the usual log scale. Look at the passband, it is very flat. Look at the cutoff frequency. The cutoff frequency is 10 to the 0, which is 1 radian per second. And notice what happens to the phase of the filter. The phase response is gradually changing as you go, and as you approach the cutoff frequency, which is right here, the phase transitions through -90 and goes all the way on the stop band to 180 degrees, which means that any signal that is getting through here in this zone, which is the stop band, is 180 degrees out of phase, which means it's inverted. All right, so that's why, that's how they stop the stop band feature is working, because it's inverted. Now if it adds back to the original signal, it's going to cancel. So that sort of helps, that phase behavior helps. If you remember the first order filter, right, if you had a chance to look at it, the first order response goes from 0 to -90, right? And we'll talk about that. We'll prove that formally in the signals class tomorrow, because it's all part of what we're doing now. Okay, so questions, we all right on that? Making sense? Yeah, I'm asking you to focus here after a long day, but making some sense? If you have any questions, let me know. Yes, we're cooking with gas. There we go. Well, of course, that is not environmentally friendly all of a sudden, that looks like. So we're going to have to even, not too sure what we're going to cook with, because if you're generating electricity using gas, then you have a carbon footprint. And if you're cooking with gas, you have a carbon footprint. I guess solar cookers, but I don't know how we're going to make some coffee in the night. So anyway, but good diversion. Yes, we're cooking. Up next, induction stoves with sun and batteries. Yep. You have any idea how environmentally unfriendly our battery is? So tell that to the people. Everything is something that I've made a point to you all about. Engineering wise, every single thing has a compromise. There's a good and a bad, and it's not just simply going from one to the other. Yeah, that's a decent project. Maybe you could put it up as a final year project in some form or fashion. Good thoughts. Okay, so how do we design the low pass filter? Well, again, the first thing, obviously, with the filter always is to choose a cutoff frequency. You choose it in radians. I compromise the environment of tomorrow for the convenience of today. Yeah. But again, it's not an easy thing. This would be a nice GP topic as an aside, but think of all the vested interest. Think of, like, in our case, the number of jobs that are vested in something that is turning out to have a high carbon footprint, namely the hydrocarbon industry. All right, and then boats and planes is not likely to get too much electric cargo vessels and electric planes in the near future. So what do we do about that? You know, so everything, it's a give and take, and you're right, we have to spread it around, and you have to take some sacrifices now for long-term gain, obviously, but it's not an easy thing at all. So back to the filter, how do you design? Well, yes, you have to choose your cutoff frequency, either in radians per second or in hertz. Our discussion and the MATLAB plots I'm using have been in radian per second, but you can convert from that to hertz always, right? Just remember what you're plotting and what you're looking at, right? So the cutoff frequency in hertz is root 2 over 4 pi RC. So having decided on what you want as a cutoff frequency in hertz, you convert it back to radians, and then you could plug it in. You choose a capacitor C2, a convenient value, typically between about 100 picofarad and about 1 micro, because you can make the adjustments now on the what do you call it, the resistor side. Once you have C1, once you have C2 as well, you make C1 twice that, and then you calculate R from, of course, the cutoff frequency. You know the capacitor value, and you could pick R to suit. So it's up to you, and that's a fairly straightforward process. All right, and if you do that, right, so this is what I wanted to compare. So let's look at something that we covered before, memory lane. If you could recall from whenever you did ECNG2011 with me or before, remember there was a class where we spoke about the general form of a second order transfer function when we were looking at the step responses of systems. And we came up with this one, right, after we manipulated some things. And we had this one, and we had this thing which is a damping factor, an omega naught, which is a natural frequency or the resonant frequency. Well, because this one is also, this particular transfer function doesn't have any zeros, it's only poles on it, 2 poles to be exact. This actually has a low frequency, a low pass frequency response as well. So if we were to take what we just derived, which is the yellow equation down there, and we express it in the form of that standardized equation above. So we divide it through by the coefficients of S squared, and then we compare the coefficients. Notice that we're going to get the same cutoff frequency, right? 1 over root 2 RC or root 2 over 2 RC, right? So it compares with that, but let me just remind you of what we had done at that point in time. Remember, we were looking at this in the Laplace domain, right, to give us an idea of what this step response of a second order system would look like, right? Especially the second order system had complex roots and had, because it had complex roots, there were certain responses. We're now seeing that that form is really the form of a second order low pass filter. So you're looking at 2 things, that the frequency response here is a low pass response that decays at the minus 40 dB per decade. But you know from what we did elsewhere that the step response now, depending on this thing here, zeta, is going to give you a response that could look like this or look like that. Yeah? If you were to calculate it through, right, there's a little error inside of here. This is actually supposed to be, just make this change for me here. Here is supposed to be 1, if I divide through here, this is supposed to be 1 over R squared C squared, right? So make that change for me on your notes right now, or whatever it is that you're looking at. Well, of course, you'll see it in the recording, but take a little look at it. Right? So if you were to do this right now, you would find that in this particular one, zeta, I believe, is 1. No, 1 over root 2, sorry. Right? If you were to calculate zeta inside of here, plug in the omega 0 into the equation for the second one, and you're going to get zeta is 0.707. Right? Remember, we said that 1 was the response that gave you. Anybody remember when in the second order system when zeta was 1? Right? We saw that was overdamped, underdamped, or critically damped. Anybody remember? It was critically damped, right? Right? So this is a little bit underdamped, right? So if you were to plug this in and plot the time response, it would be a slightly underdamped response, which means that there might be a little tendency to have some overshoot in the time response for it. Okay, why is that important? Well, again, just to clarify and to connect two things together, what we're doing is designing an amplifier, sorry, a filter. We've designed a filter, and the filter is a circuit like this. So I could get the R's, I could get the C's, I could get the op amp and put it in. The op amp is, right, you have a plus VCC and a minus VCC here, right? Or you could operate it single-ended, however you want. At some point in time, you're going to switch on the op amp. Once you switch on the op amp, if you have anything appearing here, just for argument's sake, you're going to see a step change in the input from when the power is off, V in and the op amp is seeing nothing. When you turn on the power, V in is going to see that. You're going to have a step change on the input. That step change, because of the behavior of the second order system, as it goes through the amplifier, right? Let me backtrack here a little bit. As it goes through the amplifier now, if you have that step change, it means that the output here, right, instead of doing whatever it's going to do, the output may do this and then settle to whatever it's supposed to do, right? Remember, there's a sort of, that is critically damped. So if it's slightly underdamped, it might go up a little bit and then settle down, right? So the output might kind of do something like that. This is the kind of thing that you have to be careful with, because, for instance, if this is, like I said, a hearing aid for argument's sake, what you wouldn't want is that as the hearing aid is turned on, let's say for argument's sake, right? And the recipient has it. Well, of course, they don't normally turn it on while it's in the air, but just for a hypothetical case, if it's turned on, you now have the amplitude of the signal going up a little bit before it's settling down. Well, maybe not a screech, but if for instance, if you're in a loud environment, right, or the hearing aid is listening to something, you might find the volume suddenly get above a certain amount and then settle down, which could be discomforting. Of course, think about this, using this now in something like a high-powered amplifier. So you're into music and high power audio and so on, and you have a couple of 1,000-watt amplifiers and a whole big rack of speakers and so on. And you hook up some microphones, these coming from something, and you turn on the power. That's going to give you this screech. That's the kind of thing could blow speakers and cause you no end of problems if you're not careful with it, right? A little exaggeration, but just what I'm trying to do is to connect two things that we did. One, we did in another course, which is how we came up with this equation here. And here, which is an actual circuit now that is giving you an equation that is comparable to what we just did, and to let you see that both of them could be used to give you an answer. One is giving you a time domain response, the other one giving you a frequency domain response. Make sense? Hope I'm making the connection, at least to show you that there are two things that are connected, and each of them has a different application. Yeah? All right. So, of course, like with the first order systems, we can add gain. So you could put a feedback on a ground resistor on the amplifier, and you can get some gain on the filter. For stability reasons, and we're not going to discuss that there, that's normally part of the network synthesis course. But for stability reasons, you don't want to put too much gain on the op amp, because what happens is that the damping, as we just saw, the damping which is related to R and C are also, and I guess we might need to change this here. This is supposed to be R squared, C squared here. The damping is affected by the gain of the amplifier. So that the more gain you put on, the damping tends to change, and of course R and C are also affected, the behavior of the circuit as well. So the normal rule of thumb is that usually you would not put too much gain on this particular amplifier here. If you really want to have some gain, then you run it to a second amplifier somewhere and let that do it. But the particular active filter itself, you try to keep the gain relatively small, and it's usually just to compensate for the losses of the passive part of the network. Yeah? So just a comment, but yes, you can put gain in it, and it's something that can be easily simulated just to see the behavior. Right, so we can move along now, and like we did with the low pass filter, if you interchange the capacitors and resistors, then we convert the type of filter from a low pass filter to a high pass filter. The high pass filter now, by doing that, what we do is we introduce two zeros into the transfer function. So we have two poles and we have two zeros. The general form of the high pass filter transfer function now looks like this. Some gain factor, S squared, which is the zeros part, and S squared plus some coefficient A1 omega 0 S plus B1 omega 0, where omega 0 is, of course, the cutoff frequency for the particular filter. To create the Salin key, right, or VCVS filter, and also to create the Butterworth transfer function, which we said was the maximally flat. Remember, maximally flat, the maximally flat response. It so happens, and it's not part of this, the Butterworth transfer functions and so on, we're not discussing, but you get that behavior on the high pass filter by making the coefficient A equal to √2 and B equal to 1. So when you do that, you get a second order high pass filter transfer function that looks like that equation there. And then we're going to move to the circuit that we have and do the same sort of circuit analysis that we did for the low pass case. So you do use the current, Kirchhoff's current law, and the currents into the nodes equal to the currents going out. And again, if you do that and simplify, then we get this equation down here. Right? Notice this equation, if you compare this with, let me see if I can pull it up very quickly here, what we had before. Right, look at this equation here. R1, R2, C1, C2, we have C1 plus C2 by R2, and then 1. Look at the low pass version here. Notice that the C's and the R's are interchanged. So instead of C1 plus C2, we have R, in the low pass case, we have R1 plus R2 and C2 and multiplied by C2. In the high pass case, we have C1 plus C2, all multiplied by R2. And of course, we're going to have the pole appearing on the top there. Right? So just a little way of helping you to recall the two of them. And then in this case, we do the reverse of the low pass, which is we set C1 equal to C2. All right, you remember in the low pass case, we set R1 equal to R2. We flipped around the capacitor and the resistor. So in this case, we're setting C1 to C2. We are letting R1 be R and let R2, which is this one, be 2R. And you plug that into there. Okay, and then you rearrange. So we're going to get it, after you plug it into the equation here, we are going to rearrange it to get it into this form so that I can compare this with the standard form that I introduced a section for. That is second order standard Butterworth high pass filter has a transfer function that looks like this. And the one that we just did had a transfer function looking like this. All right, if you compare it straight off, you can see that K is 1. And so therefore, it's a unity gain filter. And you could see that because, of course, we have the op-amp operating as a voltage follower, so the gain must be 1, so at least that part is correct. And then now, if we compare the coefficients now, we can quickly see that omega 0, or the cutoff frequency here, this squared is 1 over 2 r squared c squared. So you're going to get the same cutoff frequency as you did for the low pass. The high pass filter is going to be, the cutoff frequency is the same root 2 over 2rc, or 1 over root 2 separated space rc, however you want to look at it. See, I took a slightly different approach here, which was to take the standard form of the equation, get the standard form in the S domain, and then just compare the coefficients. Right, so this one we didn't take the approach where we substitute S equal to j omega and then let the amplitude equal to 1 over root 2. Okay, so two different approaches that were taken here. You could use either one. There's a standard form for the low pass as well, which we know, which is what we did in signals, and we just showed that. And there's a standard form for the high pass. In both cases, both the low and the high pass filter have the same cutoff frequency, but remember the relationship when you're drawing it. Remember the relationships between R and C for both the low pass and the high pass filter. Okay, in the low pass filter, the two resistors are the same, and one capacitor is twice the value of the other one. In the high pass filter design case, the two capacitors are the same, and then one resistor is twice the value of the other one. Yeah? And of course, this is what the normalized response for the high pass looks like, right? The high pass filter starts now, because it's the inverse, it starts at, it doesn't pass anything, and then it's maximally flat. At the cutoff frequency, it's normalized, so the cutoff frequency is 1 radian per second here. And notice the phase response. It starts at plus 180 and then it goes to 0. Remember, the low pass starts at 0 and goes to minus 180. Okay? And when we talk tomorrow, when we doing the Bode plots, we will see how that turns out. It has to do with the fact that we now have the 2 zeros. Remember, the high pass filter has 2 zeros. Right? 2 zeros and 2 poles. The poles are responsible for the, in this case, plus 40 dB per decade, right? They increase. And the zeros are responsible for this plus 180 here. Okay? All right, so have that. And everything is sort of tying together here. The design process, again, the same approach now. You take of course, you always start off with a cutoff frequency, because that's what the filter is doing, is cutting off a frequency. You choose a capacitor somewhere, again, between about 100 pico and 1 micro. Let the two capacitors be equal, and then you calculate the resistances from that. And remember that there's a relationship between R1 and R2, and you scale them accordingly. One is twice the other one. Yeah. And as we did before, we can put a gain onto it, right? So you put the amplifier and you add the feedback and the ground resistor here, and we limit the gain to a fairly small value, just to compensate for the losses in the passive network, and to stabilize everything and get our gain coming back out at the voltage level that we want coming in. So make some sort of sense? Once you do the low pass, the high pass is fairly straightforward to understand. It's the same approach. I took a slightly different form in the analysis for the high pass by comparing it to the standard equation. The low pass filter, we did both. We derived it from scratch and substituted S equal to j omega, or we used something that we knew from before, which was a standard form in the S domain, and we compared the coefficients. Both give you the same answer. Yeah? Make sense? right? It's doable, right? Of course, and you have to listen to this stuff and sit down and sometimes work it out with pen and paper as well. All right, just to convince yourself that some of the things are working. So tomorrow, in tomorrow's class now, we will cover how to create the first and second order, sorry, the second order and higher filters using cascaded sections, which is what somebody had commented on before. We'll compare it with what we did here today, and then we're going to look at bandpass and notch filters as well, and then some other little discussion as we conclude the topic on active filters. Yeah. All right, and I guess what I'll do between now as we coming down and the topics closing off now, we have one major topic again to do. Will be to sort of, as you go through, because yeah, you should be, I mean, doing some sort of revision and so on, but to sort of keep track of the things that are giving you issues that you might want some extra discussion or clarification on, because I believe I'm hoping that we have, and I think how it's turning out is that we should have, apart from the tutorial classes, at least some space to review some material and to go over some stuff that might have been giving people some issues. Okay? So keep that in mind for when we are doing that, and I'll try to collate all of that before we actually have a review session. All right? So, all right, everyone. So if we have no further questions, let me stop the recording here. Right?